Okay, in the last class we are discussing about the data transfer instructions. So we have discussed move instruction, load instruction. Okay. So the next data transfer instruction is exchange instruction. We have two main exchange instructions in 8086. One is XCHG register 2 comma register 1. The contents of register 1 can be exchanged with contents of register 2. If I take the example, so the sizes of the registers must be same, both can be either 8 bit or both can be 16 bit. So if AL contents are CC, BL contents are DD. If I write XCHG AL comma BL, after this instruction AL contains DD and BL contains CC. This simple operation. So these two contents will be exchanged. Similarly, you can write both 16 bit registers also. Then the second exchange instruction is exchange between memory and register. So the contents of register are exchanged with the memory contents. Which memory location again? So there are 5 ways to specify the memory. So if I take an example, if I write XCHG contents of BX comma AX, if the contents of AX here is 0101H, if DS is this memory, we know that for all these memory calculations by default the segment register is data segment. If this is 5000 and VX is 2000, then physical address is, we have calculated in the earlier examples also, 52000H. Here if we have some 1F, in the next location 52001H, if we have 2F. So this particular instruction simply exchanges. So this between this will be, this 8 bits will be BL and this will be BH. Here BL will be having 00, BH will be having 20. So this 00 with the lower order contents 1F, higher order contents will be 2F. So after this what happens is the contents of BX becomes BX is 2000, now it will becomes 1F, 2F, and the contents of 52000 will become 00, 52001 becomes 20. So this BL will be exchanged with this and BH will be exchanged with this. Similarly, we can have different memories. This can be base addressing mode or relative addressing mode. Okay. So we have different memory representations. So next instruction in the data transfer group is XLAT. So this instruction basically, so inside this here nothing is mentioned here, no register, no memory, nothing, but the operation inside this is AL contents. This will be operated on AL only. AL will be loaded with contents of AL plus contents of BX. The operation inside this XLAT operation is the contents of AL will be loaded with contents of AL plus the contents of the memory location pointed by BX register. So, this is actually equivalent to, this instruction is equivalent to move AL comma AL BX. So, if I take some example, if AL contents is CC, let us take say 0, 0, 1 otherwise. Basically this operation will be used for converting ASCII data into FCD data, say 31H, and DS is take same 5000, BX is 2000 and 52,000, the contents of 52,000 location will be say F1. So, after the execution of this one, what happens is, before the execution of this one, if I write XLAT, the contents of AL becomes contents of AL 31 plus contents of the memory location pointed by this, whose physical address will be now 5200. So, the physical address of this one we have already discussed several times this one. So, 52,000 H, the contents of this 52,000 is F1. So, this instruction basically, so this contents of BX means this is the address, with in that address some data will be there. So, what will be this? F plus 3, F plus 1 is 10, 11, 12. So, 1, 2, 2 F. So, basically this particular instruction will be used for converting ASCII code into FCD code. ASCII stands for American Standard Code for Information Interchange. Whereas FCD keys extended binary coded decimal, interchange code. So, among the various codes, so these two are ASIC and FCD code are famous codes. So, ASIC is a 7-bit code. So, what is basically this? So, you might have heard about the ASCII keyboard. So, what is meant by the ASCII keyboard? So, each key will be coded by ASCII code. So, this ASCII code is a 7-bit code. We have 8-bit code also. This is a 7-bit code. So, we know that using 7 bits we can have how many combinations is 2 raised to the power of 7 combinations, which is equal to 128. Means if I use the ASCII code to code the keyboard. So, if you have the keyboard here, so I can have 128 different keys. So, total number of keys will be in this keyboard, we can have 128 keys. correspond to each code. If I have 7-bit code, if all 7s are 0 0 0 0 0, this is correspond to 1 key. If this is 0 0 0 0 0 0 1, correspond to 1 key. So each key will be having unique code. So like that, if all bits are 1, it is correspond to the last key. So in case of ASCII code, 0 will be represented by, this is standard, means which is equal to 0 1 1 0 0 0 0 30H. This is in hexadecimal, even you can insert this 0 here. So this will be equivalent to 30H. 1 will be represented by, this is 31H. So on up to 9 will be represented by 39H. Of course, for these 3 we require 4 bits, we can insert 1 0 here, so to express in hexadecimal form. This is about the ASCII code. So similarly we have extended binary coded decimal. So why this many codes, keys are required? If I use a 6-bit code, initially there are computers with 6-bit code, which is called 6-bit internal code. So using 6-bit internal code, we can have how many different keys? 2 raised to the power of 6, which is equal to 64. But in this keyboard, so we require all lowercase letters A to Z, which is 26, uppercase letters A to Z, 26, then we require digits from 0 to 9 is 10, then we require some special characters. Such as dollar, we have greater than, less than, different symbols. And so if I use only a 6-bit internal code, so we can have only 64 different keys. So these 3 together is 62. So we can have only 2 special characters. Okay. So to include more special characters, we will go for the more number of the bits. So this ASCII is 7-bit code, we can have 128 different characters. So out of that 62 will be to represent the lowercase and uppercase alphabets, and 10 for decimal digits. So remaining we can have up to, so 128 minus 26, 62 is 6, we can have 66 special characters. So that is why we will go for ASCII code. Even if you want more than this special characters, more than total 128 bits, we will go for extended binary coded decimal, EBCD IC code. This is 8-bit code. So using this we can have how many keys? 2 raised to the power of 8, which is 256 different keys we can have. Keys can be incorporated in EBCDIC keyboard. Okay. Now in EBCDIC, if I take say 0, 1, so on up to 9, this will be equivalent to, this is F0, which is 1 1 1 1 0 0 0 0, which is equal to F0H. 1 is equal to F1H. So on up to F9. They are standard, which is defined by inventors. Similarly, we have for lowercase letter some code, uppercase letter some code. Now this particular XL80 will be used to convert ASCII code into EBCDIC code. So correspond to 0, this is the EBCDIC code, correspond to 0, ASCII is, so we have seen in the last slide, is equal to 30H, EBCDIC is F0, 1 is 31, F1, so on up to 9 is 39, F9. So what is the relation to get the EBCDIC code from the ASCII code? So how much you have to add? This is 3 and this is F, you have to add 12. So means F0. If I add 30H plus C0H, this will be F0. This is 30H plus C0H. So C plus 1 is D, E, F, F0H. Similarly, if I add C0H2, so all these values, you take any value and if you add 30H, you will get these values. So in XL80, how this conversion can be performed? So what I will do is, so I will take in AL first the code corresponding to ASCII, which is 30H, and if I take say DS is equal to 5000, BX is equal to 2000, and in 52,000 I will store the value which is to be added to get FCDIC from ASIC. What is that value? Is C0H. So if I write XL80, what will be contents of AL? As I have explained, AL will be contents of AL plus contents of the memory location pointed by Vx. So this will be equal to AL contents are 30H plus this is contents of 52,000H, contents of 52,000. So this is equal to 30H, the contents of this one is C0. So you will get F0H. So before the execution of this in AL we have 30H, after the execution we have F0H. So you see, 30H is the ASCII code corresponding to 0 and this is FCD code corresponding to 0. Similarly, if I want for 1, we can store here 31, if I store 32, 33, you will get corresponding this. If I change this to 31, you will get F1, 32 we will get F2, 33 we will get F3. Like that we can convert ASCII code into FCD code. So you see the importance of this XL80 instruction. So these are all about the data transfer instructions, the first group. The second group is arithmetic group, arithmetic instructions. In arithmetic we will discuss about addition, subtraction, multiplication, division, increment, decrement. These are the various arithmetic operations. First I will discuss about the add instructions, addition instructions. So there are 4 addition instructions, without carry, 4 with carry. So the first addition instruction is add is the mnemonic. We can have register slash memory 2 comma register slash memory 1. So we can add the contents of this register or memory 1 plus contents of register slash memory 2, and the result will be stored back to the register slash memory 2. This is the internal operation. Both cannot be simultaneously memories here. Remember that both cannot be. So memory to memory adding is not allowed. So both cannot be memory. Memory to memory addition is not allowed. So one of this one must be a register. So if I take the examples, add AL comma contents of BX. So, by default the physical address can be computed by using DS. If this is same as the previous example 2000. So, in this 52,000 if you have CDH say, and this AL contains say 15H. So, after the execution of this instruction, what happens? What will be the contents of AL? AL will be sum of this CD and 15, because the physical address of this one using this DS and BX will be 52,000. So, CD plus 15. So, D plus 5 will be, D plus 1 become E, D plus 2 will be F, D plus 3 will be 10, 11, 12. This will be 12. Another way to find this one is D nothing but 13, 5, say 18, 18 if you convert into hexadecimal, 18 1s are 18, 2 is the remainder, 18 zeros, 1 is the remainder. So, 1 2 is the hexadecimal of 18. So, in decimal this D is 13 plus 5 is 18, in hexadecimal is 1 2. So, C after that D E, so this is E2. So, this will be having E2, carry flag will be reset. So, this particular addition instructions affects all the flags. Similarly, if you have here 16-bit register, it will take from 2 consecutive locations. Okay. So, lower order will be added with the first location, higher order will be added with the second location. Similarly, you can have, so this side memory, this side register, the same thing, but result will be stored in memory. Now, the result is stored in AL. If you have add BX comma AL, then this result E2 will be stored in this 52,000H. So, one of these two operand should be register, both cannot be memory. This is a simple add instruction. So, the second add instruction is add register with data. If this is 8-bit register, 8-bit data, 16-bit register, 16-bit data. So, directly the data will be added with register and stored in register back. If AL is having 32, if the data is, if you give write the example, add AL comma FF H. So, these two 32 and FF will be added, result will be stored in AL itself. This will be 1011, this is 1013. So, this is carry flag is set, the result will be 31, because AL is only 8-bit register, this stores only 8-bit. So, this 31 will be stored in AL, but the carry flag will be set. Okay. This is about add register comma data. Similarly, we can have add memory comma data. We can add directly some data to the contents of some memory location. Again, that memory location can be addressed by using either indirect addressing mode, direct addressing mode, based addressing mode, indexed, based index. Okay. So, these are the 3 add instructions, and then there are 3 add instructions with carry, they are without carry. For example, if you want to perform something like, if I want to add multi-byte numbers 7255 4F32H plus F210 FECAH. See here what happens if I want to add this using the byte, or even if I use 16 bit at a time, because 8086 is 16 bit microprocessor, it can perform this 16 bit addition in a single clock cycle. Okay. So if I perform this, what happens here? This A plus 2 becomes C, C plus 3 become F, F plus E becomes 1D, and this becomes 1 4. So in the first cycle it will add these two numbers. Now in order to add these two 16 bit numbers in a single clock cycle, it has to add these two along with the carry which is generated from previous stage. So in order to perform this type of addition, we require ADC instruction. We can have ADC register slash memory 2, same the first one, comma register slash memory 1. Both cannot be memories. The operation is here, register slash memory 2 will be added with register slash memory 1 plus the status of carry flag is also added and stored in register slash memory 2. Similarly, you can have correspond to this ADC register comma data. Here the operation is register plus data plus the status of carry flag will be added and stored in register. The only difference between this instruction and this instruction is here an extra thing is carry flag. If carry flag is reset 0, then both ADC and ADDR both are same. And another sixth instruction is ADC memory comma data. Then also same thing, contents of the memory pointed by one of the addressing modes plus data plus status of the carry flag, and the result is stored in memory. So there are 3 add instruction without memory, 3 add without carry, 3 add instruction with carry. There are total 6 add instructions. Similarly, we have 6 subtraction instructions, 3 without borrow, 3 with borrow. The mnemonic for this one is SUB, same register slash memory 2 comma register slash memory 1. So both cannot be memories, all the flags will be affected here also. So in place of plus we have to write only minus. So this is this minus this. Will be performed, result is stored back into register slash memory 2. Similarly, we can have sub. I am not giving the example because they are similar to the addition instructions. We can have register comma data. So simply the data that is specified in the instruction will be subtracted from the register and the result is stored in register. You can have sub memory comma data. There also the contents of the memory location specified by the given addressing mode will be subtracted data and the result is stored in memory. Similarly, we have 3 with borrow. In subtraction, we require borrow in some cases. SBB register slash memory 2 comma register slash memory 1. here register slash memory 2 minus register slash memory 1, then carry flag is also subtracted. So, in case of ADC carry flag is added, in case of subtraction with borrow carry flag will be subtracted, because we know that so for carry flag to be set during the addition carry has to be generated, during the subtraction borrow is required, means if the subtrahend is more than the minuend, then the borrow flag the carry flag will be set, there is no separate borrow flag. So, that is why the carry flag status will be subtracted here. This will be stored in register slash memory 2. Similarly, the case with the other two instructions, SBB register comma data. So, register contents minus data minus carry flag is stored in register. Next one is memory comma data. So, data is subtracted from the memory along with carry, result is stored back to the memory. So, just 6 subtraction instructions. Then we have multiplication and division instructions that we will discuss in the next lecture. Thank you.